Welcome back, ladies and gentlemen. Talking about impulse and momentum. Let's hit momentum first. Basically, momentum is a property of objects that is related to mass and velocity. We're using lowercase p for the symbol of momentum, and quite simply, it is equal to the mass times the velocity of the object. Now, you're going to look at this and say, well, that sure seems similar to this other thing that has mass and velocity in it, and that was kinetic energy, right? Similar, but obvious differences with the exponent and the coefficient in front. With momentum, the units will be, well, we got mass, which is standard kilograms, and velocity is meters per second, and when you do that multiplication, you get kilogram meters per second. Unfortunately, that doesn't combine into something nice, like how all this mess combines into joules for energy, for kinetic energy, and also the other forms of energy. We still just are stuck with kilogram meters per second for momentum. Now, that's basically it. You know, if you're talking about two objects moving at the same velocity, but one has more mass, the one with more mass will have more momentum. You can almost think of this as how hard it is to stop it, which is going to sound confusing because that's going to make it sound like inertia. If it's moving, it's got a lot of inertia, then it's going to be hard to stop. It's going to be hard to change what it's doing. Well, yeah, because essentially, if you think about this, mass is how you quantify inertia. It's how you measure inertia. Oh, yeah, okay, cool. But if it's going really fast, then it's also going to be hard to stop it. Is it hard to change the velocity a little bit? Well, that depends on the inertia of the object. Is it hard to change the velocity from whatever it has to zero? That does depend on velocity because you're talking about the size of the velocity change as well. So, well, where does this come from? What's it good for? With energy, and also work is related to energy, right? We were able to analyze when work is done, particularly with total work. Well, that's going to cause a change in the kinetic energy of the object. Awesome. But that work is done over a distance. It's kind of a slow process. It takes a given distance, a substantial distance, to do the work, and that's where you have an acceleration over a period of time and you change your velocity. Good stuff. But here, with momentum, we look at momentum because it's very easy to use momentum to talk about collisions, the impact of one thing with another. It could be a car crash, could be the impact of a basketball with the floor of the court. It could be the impact between two football players coming off the line and trying to tackle each other or just trying to block each other. It could be anything. So with collisions, you want to really focus on momentum, particularly because it allows you to find the force of the impact. Whereas talking about this with work and kinetic energy, you really can't do that. You can talk about what's going on beforehand, what's going on after the impact or the collision, but not during the collision. It doesn't really work out. Okay, so what about momentum? Sort of where does it come from? Let's check this out. Newton's second law says that force, and particularly, I really am supposed to say net force, but you know what I mean, is equal to mass times acceleration. If you break up acceleration, it's basically change of velocity divided by time. Easy enough. Change of velocity is final minus initial velocity. Okay, fair. And when you sort of rearrange this a little bit, you distribute the mass and you multiply both sides by t, so bring the t onto the left side. You've got mass times final velocity minus mass times initial velocity, and that's equal to force times time. Well, a mass times a velocity, we know that's a momentum. So you've got final momentum minus initial momentum equals force times time. So force times time equals change in momentum. So we give this a name right here on this side. You remember that we were talking about energy, the equivalent with work and energy. Well, what is it that changes kinetic energy? Total work. And here, what is it that changes momentum? This thing. And we call this thing impulse. So work and impulse are sort of cousins of each other because they both change a property of a moving object, right? And it's interesting that the work is more or less equivalent to a force times a distance, where an impulse is a force times a time. That's kind of neat to look at it that way. They're sort of parallel, sort of cousins of each other. So, how does this help us? If you're interested in finding this thing called the force of impact, or the force of the collision, well, it's very easy to see that you can find the force here. Let's bring that T back on the other side. So, like that. You might call this the force of impact equation. I actually don't know if it has that kind of name formally, but you can think of it that way. Another way to think of this is that it's almost like looking at Newton's second law in a different way, where at first we learned that a force is equal to mass times acceleration. Here we see that a force is equal to the rate of change of momentum. And in fact, if you put this in calculus terms, and we're not going to, but if you did, this is actually how Newton first expressed his second law. Derivative of momentum with respect to time is, I believe, how you would say that. But never mind that. That's not really part of this course. But that's interesting to see Newton's second law. It's really the same thing, just with looking at it through a different lens, if you will. Okay, so that's where this idea of momentum is sort of ultimately comes from. You know, we derive this idea of momentum and changing momentum, and also this idea of impulse. It's from Newton's second law. But what about this? Well, let me create some more space here. I want to show you something. Let me see if I can make this happen. Just these basic steel balls. So, try to create a collision, because it's in analyzing collisions or impacts that momentum is very, very handy. Oh, complete miss, fail. There's a little bit of one, and you could see something really interesting. When they come together and they meet and they don't strike head on, they kind of come off like this. Very similar to playing billiards or pool. Oh, that was neat. That one just kind of bounced right backward. So, what's going on? Now, I have some static images I can show you to help understand this a little better, perhaps. Two cars headed toward each other, and let's say they're going relatively slow. They're going to collide. Velocity this way and a velocity this way. Velocity of car 1, velocity of car 2, and they're small velocities, so there's no damage to the cars. A tiny little bumper on the you call it a fender bender, except we're not bending the fenders. It's even smaller than that. They're going so slow, and so this car also has mass of car 1 and mass of car 2, and they sort of do bump. But what we're going to see something is interesting. So car 1 has its own momentum, right, because of that mass and that velocity. Momentum of car 1 and momentum of car 2. Now, this idea about momentum is cool because momentum is a conserved quantity. And what that means is you don't end up with a different value of momentum after an event compared to what you had before. Well, what's the momentum we have before the collision? Well, it's equal to the momentum of 1 plus the momentum of 2. So here, total or net momentum is momentum of 1 plus momentum of 2, right? And they're going to collide. Well, since momentum is conserved, the net momentum has to remain the same. In other words, there will be no change in momentum. So this net momentum beforehand, you can consider this your initial momentum. And since there's no change, your final momentum must be the same. Now this is cool because it lets us realize the final momentum is made up of the momentum of car 1 and the momentum of car 2 after the collision. And we can find each of those from a velocity and a mass. I'll put my subscripts in there to stay consistent. This is neat. What's going on is this. Two cars come together and they bump, but it's a collision that does no damage, and they simply bounce off each other and move away slowly. And so check this out. If the momentum beforehand, the initial, must equal the momentum afterward, and nothing else is going on, then, well, what about these velocities? If the masses are the same, and the velocities are different, you might say that V1 is just a little bit larger than V2. What's going to happen, this is kind of interesting, we're going to see that afterward they sort of swap velocities if M1 equals M2. And what we see now is that they just kind of rebound and they kind of trade velocities. But why do we have conservation of momentum? Why is initial equal to final? Well, it turns out in a situation like this, there is a force taking place right here during the collision. It's true. You do have this taking place. There is a force. And you could look at the change in momentum of car 1 separate from the change in momentum of car 2. But if you look at the total momentum of the system being both cars, before and after, it is unchanged. And it gets complicated because there's a lot of math steps to go through. But it isn't so bad. None of the math is terribly difficult at all. But the point is this. There is this force of collision. They come in like this, and car 2 exerts a force on car 1. Car 1 exerts a force on car 2. But the thing about those forces is they are internal to the system. They don't come from anything outside the system. Well, you're going to say, Woods, of course. Gravity is pulling down on each car, and that's coming from outside your system. True. And the Earth is also pushing up on each car, and that's coming from outside the system. And those forces balance. They cancel out. So, and the same thing down here, that's unchanged down here too. So we get to say, we get to say that momentum is conserved put the box around it to sort of highlight it, make it stand out. Momentum is conserved when all external forces, losing my marbles over here, when all external forces are balanced. Another way of saying that, let's just fit it in. In other words, the net external force is 0. Okay, then momentum is conserved. If you had some external force not part of your system, momentum would not be conserved because the momentum of the whole system would change. So now what if you expand your thinking big enough? You go, wait a minute, how big of a system can we talk about? Can we talk about the Earth as well as the cars? Yes. Can we talk about the solar system as well as the Earth? Yes. Can we talk about the Milky Way? Yes. And in fact, you can talk about the entire universe. And it's a hard thing to envision. I would argue really impossible. But you could say, well, think about this. There's nothing external to the entire universe. And so there can be no external forces acting on the entire universe. There are only internal forces acting on the entire universe. What that tells you is that the total momentum of the universe cannot be changed. And that's a true statement. The total momentum of the universe is a conserved quantity all the time. So if one part of the universe gains momentum, another part of the universe must have lost momentum to conserve that momentum. Enough of that mess. Now, let's wrap this up. What do we know? This is probably page 4. What for keeping track of stuff? Momentum is conserved. when the net force on the system is 0. So also we know momentum is a vector quantity. So think about this for a moment. We go back to the original idea of momentum, mass times velocity. Velocity is a vector, its direction matters. And the same thing with momentum. And this is a big important difference between momentum and energy. Energy is not a vector. There is no direction to energy. So you cannot ever add energy to energy and have it cancel. Oh, but you can do that here. It is possible, like with forces, to add momenta together and get them to cancel. It's a vector quantity. That's very important. There's a way to write momentum. You can add individual momenta of a system together and you get what's called the net momentum, just like with forces. When the change in the net momentum is 0, well, you've got conservation of momentum. It's conserved, right? And all this tells you is that when you add every little bit of the system together, so we had a car going that way, and we had a car going that way, what's the total momentum of the system? It could be 0. You have an mv that way, you have an mv that way. If masses are the same and velocities are the same, they're just opposite direction. And you've got the momentum of 1 and the momentum of 2. And when you add them, because of the negative nature of one of them, you're going to get a net momentum of 0, right? And what that means is, after the collision, the net momentum must still be 0. No change. But the momentum of an individual part of the system can change. So you're going to see that in problems you're going to be solving. You're going to see that in collisions that are happening, and both in examples in the textbook and also in lab. And it's a really good thing. Momentum, I think, overall is easier to deal with than energy. I think it's a little bit less complicated in general. However, some of the math will get interesting for us. Okay, that's it for now. Thanks for watching. I'll catch you next time.